I thank everybody for being here. I know that we are very close to Pujol. It's a big holiday for us, and many of our students are probably ready for that, and maybe possibly gone back home already. But thank you all for being here. We're going to videotape your talk, and we're going to put it on the YouTube so that students who have missed it will be able to see it. Okay, today I have a very distinguished guest, and I'm very happy that he's here. All the way from San Diego, UCSD, Professor Alex Oregolu. And let me just say a little bit. He's going to be talking about VLSI system for testing, reliability, software in general for embedded systems. I guess he's very mathematical, and he's also a software-oriented professor in the computer science department. And he's going to talk about high-level software to test systems, hardware systems. Let me just say a little bit more about him. He's been a professor at UCSD, University of California, San Diego, very highly reputable university. He's in the computer science and engineering department, and he went to undergrad at Harvard, studying applied mathematics. And then after his graduation, he went to UIUC, University of Illinois Urbana-Champaign, where he studied applied mathematics again and got his PhD. And from then on, I think he went to UCSD. He is, was IEEE Computer Science Distinguished Lecturer, and he's written a lot of papers. He's also have wonderful students who are doing very well at various universities. Okay, let's give Professor Oregolu a big round of applause for his wonderful talk.
Thank you, Professor Chan. So thank you all for coming here today. I know, I have rough competition with my talk because New Year's is coming.
You cannot beat that.
But I guess, one thing that I understand is usually at the end of the old year, you want to clean up all the bad things. And then the new year will bring many good things. So since I'm at the tail end of the old year, just think about this as a bad talk, and then I'm sure you're going to get much better talks next year. So I promise to give you a bad talk. No. So, Professor Chang mentioned that I do many things. I've been at UC San Diego for quite a while. So I have been there now almost 40 years.
Wow.
And throughout my career, one very dominant part of my research work has been computer-aided design, and within computer-aided design, particularly the question of how do you test chips that are being manufactured and make sure that these guys are reliable and you send them off to your customers and they do well and people don't come knocking at your door and saying, my car crashed because of your stupid chip and stuff like that. So that has been a big focus. And I've gotten into many other things because in 40 years you can't just keep doing one thing. And I've been involved in computer architecture, embedded systems. More recently I've been doing also some hardware security work. But today I'm going to talk to you a little bit about something that is a newer work because, of course, as you know, and who hasn't, artificial intelligence has been very important. It has redefined the landscape of what it means to be a researcher in computer science and electrical engineering. So I have also, together with my students, thought that if we look at the reliability issues involved in these particular parts, it would be a nice thing and a nice contribution to the field. So we've done that, and the work has a little bit of a different texture than the traditional work that I have done in terms of VLSI testing. I mean, VLSI testing has, of course, many, many different parts. So one thing, and I'm going to try to explain to you why, is that you need to take a little bit of a more high-level approach to the reliability question when you deal with artificial intelligence systems. So that is one of the things that we're going to be talking about today. Now, the talk also has a second part, and the second part has to do with hardware efficiency of artificial intelligence systems. So they're both a little bit hardware-oriented perspectives on the question of how you execute AI systems. But there is a question of the efficiency of these particular systems. And what I wanted to do over here is also give you some perspectives and some research work in terms of resource efficiency that we have done in this particular work. So this is the confluence of the two things that we're going to be talking about today. Now, as Professor Chang mentioned, there is a lot of work that my research lab has been involved in that is more traditional semiconductor testing. As a matter of fact, a recent work of mine has to do with adaptive test issues. There is also some hardware security and how to do Trojan detection and logic obfuscation and issues like this. And perhaps some other time when I'm in Korea or in this wonderful city of yours, we can go over them. But today we're going to concentrate on this particular part. So with this, I'm going to start. And I did have one question, Professor Chan, for you. I know it's 11 to 12. Is the 12 o'clock cutoff a real cutoff?
Definitely. Well, I mean, that will be the preference because, you know, it's lunch times.
So I better,
yeah.
I think you're going to lose your speaker.
Yeah, we should. I didn't realize that it was there. Sorry about that.
That's the second time. Okay. All right, maybe I'll stay at a safer place over here. All right, so let's talk a little bit about, I mean, of course, as you know, with deep learning success, in the beginning we had a little bit more image processing kinds of applications, which gave a lot of impetus to this particular field. And now, of course, I mean, with ChatGPT, all this natural language processing is very important. Voice recognition along the way, a little bit maybe a low-stakes game with recommender systems. And for whatever it's worth, all these deep fakes, have become very successful and popular in this particular field. So this is partly the success of this particular field. But there is also a subpart of this particular field that is particularly concerned about some of the issues that my talk will cover. And this is when you look at the edge applications. And of course, there is many edge applications. I mean, autonomous driving is a very important field. Robotics, industrial control, military defense, and of course, more and more healthcare, automated healthcare and surgeries are important. Now, what is the important thing over here? Well, the important thing over here, there is really two concerns. One is the chips and the hardware is being exposed, and therefore there is certain amount of increased vulnerability of the system. And the second thing is, by being at the edge applications, you can't quite have as much hardware as you want, because these are very constrained systems resource-wise. So consequently, you need to worry about reliability, and you need to worry about efficiency in this particular system. Now, while you need to worry about these particular issues, particularly if you look at the issue of the resource efficiency, what you see is that the field has been blowing up in terms of the amount of resources that it requires. And you can see the exponential curve over here, and the top over here shows the ImageNet accuracies. The accuracies have been increasing, but at the same time, the number of parameters has been increasing. All right, the number of parameters has been increasing exponentially, but go down to the bottom graph on the left of this slide, And you will see that those numbers are growing dramatically. I mean, you know, this is when we look at the natural language processing systems, and GPT-3, which by now is passé, 170 billion parameters over there, and GPT-4, I mean, you know, there is numbers quoted from 1 trillion to 150 trillion parameters and issues like this, depending on the particular version of what you're looking at. So that puts huge amount of pressure on the memory hierarchy and how to move things around. Now, also doing all these operations and all the flops that this requires has strict computational demands. So from a resource efficiency perspective, this is a very vibrant question. And people, of course, have been looking at this question, and they have taken different perspectives on this question, starting from the hardware perspective. So we have domain-specific accelerators, we've got novel technologies, I mean ReRAMs, and of course more advanced memory solutions. On the software side, we've been looking into neural architecture search. And then there is things that sort of combine software and hardware, particularly software methods that look into how to improve the efficiency of hardware. One of them is reducing precision, and the other one is maybe reducing the number of parameters, because most parameters at the end of the day are not quite doing anything for you, but they're just sticking around, and maybe if we can cut them off from our lives, we'll have fewer parameters, less memory, and stuff like that. So these are enticing agendas, but these enticing agendas come with certain problems that we want to look a little bit more carefully as we look into the hardware-software synergy, which is what we're going to be looking at the latter part of this particular talk. Now, from safety and reliability perspective, of course, safety and reliability has been with us throughout our journey and forays into the semiconductor world. And there has been many solutions in the last 5, 6 dozen years. And the problems, you know, we start about thinking about high energy particles, and there is also issues when you manufacture. You just simply get permanent defects. You also get transient defects. You get intermittent defects. And then there is other issues that your chip may be very good. You put it in the car, and 6, 8 months later, I mean, the chip is starting to misbehave. So there is all these aging issues, there is bathtub curves that people talk about, and how to shake up these aging-related effects. And there is delays becoming more and more important and not meeting the clock cycles and issues like this. So these are issues that have been with us throughout our journey in semiconductors. And of course, many solutions have been suggested, ranging from hardening the circuit. In the architecture level, there is a whole important mathematical field of error-correcting codes, how to detect the errors, how to restore the misbehaving situation over there. And a lot of times, I mean, the codes are expensive, but even more expensive are techniques that are very comprehensive, but very expensive when you duplicate or triplicate the particular chip or the hardware, and particularly in places where human lives are in concern, like airplanes and stuff like that. You want to make sure that the doors on your airplane have all the screws screwed in so that the door doesn't blow up and stuff like that in that particular case. But they're expensive. Now, the similar things, the replication kinds of ideas, are also in software where we see M-version programming, where you sort of try to have the same program written multiple ways and compare the results. So that's a different kind of replication, but it has similarities to the modular redundancy. And of course, there is checkpoints and recovery where you can go back once you detect errors. All these have large area, power, and efficiency constraints. So this is the lay of the land. This is what we're looking at in a nutshell. So now the question in front of us is, okay, I mean, this is the situation at a very high level in the world of semiconductors, and particularly in the world of AI hardware, where the questions are accentuated because we need so many more resources. And also remember, I talked about, you know, regularity of the hardware and stuff like that. That regularity makes things very efficient, but that efficiency comes at the cost of putting things denser and denser, and therefore there is going to be a lot more problems with reliability of this particular circuits. So questions need an answer. But when you look at a particular new field, you can try to do the old stuff and do it better, or you can sort of sit back and sort of say, well, what's new in this particular field? And how can I take advantage of the new novel stuff over here in order to twist it and use it for my own purposes to solve these problems that I'm seeing? All right? And if this is the perspective over here,
Be careful.
and if this is the perspective over here, it behooves us to look into some of the characteristics of AI systems. And I'll give you three. I mean, there is many more, and we can get into philosophical discussions about these fields. But, you know, in the short amount of time, let me point out redundancy. The systems are highly redundant. And you may say, well, I mean, we can do better, can't we? And I will suggest that actually you need the redundancy, because the systems have to find their way to your solution. And in order to manipulate in that space of search, you need the redundancy, and the redundancy will come with you. And you can see over here that the capacity and the total capacity and what you need is, you know, much different as when you look at it. And part of the reason is because of the plasticity of these systems. Now, the plasticity of the systems means that you are looking for the solution, and there is many solutions, and this particular solutions over here, and this particular solutions over here.
Can you use the mouse? Maybe
That's what I was looking for, and my good friend Kambin gave me the mouse, but now
What is the mouse?
I have lost it some. Oh, here, I found it, Kambin. I had left it over here. So, and then, you know, in this program subspace, you have to search and train in order to come to a particular solution. And there is not really even a single solution. There is many solutions out there that will do pretty much the same quality job at the end of the day. So there is a lot of plasticity. You can search in different ways and try to come to an appropriate solution, and some of those solutions may be better for you in terms of resource efficiency, they may be better for you in terms of reliability and stuff like that. And this is another thing that we want to take advantage of. So, and then the third thing over here, and this is particularly important, is the resiliency. Now, this is a confusing thing, particularly for those of us who are looking into reliability, because when I started looking at that particular point together with my students, the first thing that we ran into was, well, aren't AI systems naturally resilient to faults? And it turns out the answer, like every answer in life, is yes and no. So yes, they are resilient to faults, but they are resilient to small faults. Most small faults will not do anything. So if you sort of hit the least significant bit of some 8-bit representation over there, chances are you won't really have an accuracy degradation at the end of the day. But if you hit the sign bit, or if you hit the most significant bits, chances are you will hear about it, and you may even have the wrong classification or whatever you are looking. So the question becomes, how to structure systems so that this resiliency, the natural resiliency, you can take advantage of in order to deal with the real reliability problems that you're going to run into. So 3 high-level ideas: the redundancy, the plasticity, and the resiliency to these particular faults. And these are algorithmic high-level issues. And then there is also, from a hardware perspective, there is also the regularity. Now, this regularity is provides a lot of opportunities for effective testing. It also provides a lot of opportunities for yield improvements, because when you've got this regular substrate over here, if one of those guys breaks up, maybe you can do the job with somebody else over there. Now, of course, we know this particular perspective in the world of memories. Memories are very regular. And we put extra rows and we put extra columns and stuff like that. But here the question is a little bit different. It has to be formulated a little bit differently in order to take the yield improvement perspectives and benefits into question. And towards the end of my reliability part, I'm going to talk to you and show you how we can do some of this. But I think there is many opportunities out there to exploit both the hardware and the software ideas. Now, let me give you, before I delve into the nitty-gritty of this particular technical work, let me give you some high-level characteristics of how we approach it. And I'll give you 4 tiles over here. The first one is, we are in the business of reshaping software. So what this particular thing means, as I mentioned before, the whole process of training neural networks is searching in this particular space, and there is many different effective solutions. So how do we identify a target program that is great for us in terms of reliability or resource efficiency is one of the questions that this work tries to answer. The second part is to enhance the hardware. So what we want to do is we want to do some very small, tiny modifications to the hardware that will yield a lot of improvements in multiple ways. And there's 2 different approaches rather that I'm working on. One is the modular extensions. You can put a little bit of a modular extension to guide certain things, as we're going to see. Or another part may be a little bit strategic modifications, like control modifications of the hardware that we're going to be seeing. Issue number 3, forget about making sure that everything is working the way it was supposed to be working. Now, this is a high-level departure from the world of semiconductors, guys. I mean, you know, before, the way we define semiconductor correctness is that everything is supposed to work according to the high-level specifications. In AI systems, we don't care about it. I mean, the defining coin of the realm is the fact that you can get the accuracy you want, but not that everything is according to the specifications over there. As long as you can get the accuracy to match, then I think you're doing well. So the important thing over here is functional correctness rather than structural correctness that you're going to be running into. And the 4th thing is utilize the statistical nature of AI methods where the accuracy is never going to be 100%. So it provides a lot of potential for approximate techniques at low cost. So those are 4 different high-level approaches to our technical work. And with this, I'm going to take you through one more high-level bit, and then I'm going to show you some of the technical approaches very quickly, I hope, in the remaining amount of time. But let me also spell out the technical challenges. Because, you know, it sounds like, okay, you put some modular extensions, you take advantage of functional correctness, aren't we done? And the answer is, of course, far away from it. There is many, many technical challenges that need to be addressed. And one of the things that I want to bring in front of you and give you a little bit of a taste is to tell you some of those technical challenges at an abstract level. So let me try to motivate this particular part over here. And this has to do with the resource efficiency issue. And so what we've got over here is, let's say, a constrained sparsity pattern. So sparsity, as you, I'm sure, have heard, is that, you know, when you do the computation, you don't need all of those computational nodes to be operating. So consequently, you may find yourself in a situation where you only need a certain subset. Now, some of you will have noticed that this particular subset over here with the nice colors and the blue and the yellow has a particular pattern. And there is particular patterns that we're going to get into as we discuss this particular piece of work, but I don't want to get too much into the nitty-gritty details yet. So for a moment, let's say we want something like this to happen for whatever reasons. Now, how do you approach this particular problem? And there is the traditional way of approaching this particular problem, and the traditional way of approaching this particular problem. How do I make this friend of mine go away from me? And while you're helping me, I'll have another sip. So the conventional approach over here is, you train this without the constraints. Without the constraints of this nice structure over here. And then once you have trained it, you do post-training enforcement. And the post-training enforcement will deliver results for you, but with a lot of difficulty to get good results. Because it doesn't know in the beginning that this is what you wanted. What you wanted only comes afterwards. And it's incompatible and conflicting with the pre-training objectives. So consequently, you get limitations on effectiveness, you get limitations on the quality of results, and stuff like that. So instead, a novel perspective may be to somehow be able to tell the system during training that this is the structure you're angling for, and have the system evolve in the search space around a solution that has some of these characteristics. Now, that comes with challenges. I promised you that there is challenges here. So this is not the advertising of the solution, but rather telling you the challenges. So let's look at the challenges. One of the challenges is that while you are training this, there is going to be competition across the variables, because here, in every row there is only one guy, and in every column there is one guy, and in every row there is one guy. So at any particular point, the variables over there may start competing with each other for grabbing that particular position. So this is one challenge that you run into. So you need to think a little bit how to design the constraints. And the second thing is the gradient flow issues in training, because only some of those guys will be doing anything at a particular point, but still you need to have the ghost of the others in case at some point you had to resurrect and rearrange the whole arrangement over there. So you need to worry a little bit about gradient estimation policies and stability of the system and stuff like that. So this gives you a little bit of a taste of these new methods and the challenges that they bring along. So let's move on to the technical work. And in the technical work, I'm going to give you a little bit of the highlights of a number of different things. And I'm breaking it down into two rows. The top row is the safety and reliability, and the bottom row is more the architectural resource efficiency issues. And then I'm also breaking it down into column-wise into a matrix over there, post-training or training integrated. So the post-training is after training. So this is more akin to the conventional method. You let things be trained and then you muck with that. And the other one is more what I showed on the right-hand side, the training integrated method. All right, so who are the pieces? Now, post-training reliability. So what we're going to talk about is hardware error detection via external invariants. And then in terms of training integrated, a couple of different approaches over here. Hardware error detection through embedded internal invariants. And then those will be a little bit extended to do cost-effective rectification of hardware errors. And then we're going to change our perspective in terms of reliability to a proactive method. And the proactive method is to reduce vulnerability of the system before you do anything. And this has to do with designing error-resilient DNS. So you want to design them in such a way that even if faults happen, the faults will not really have an impact on what you are going to be doing, instead of correcting the errors once the errors have appeared, which is more the perspective of these top guys over here. So the last bit over here has to do with the question of yield improvement. And the yield improvement has to do with cost-effective hardware defect adaptation. So, and I'm going to show you over there ideas about regularity and how you can take advantage of this in order to adapt to the defects that are happening. So these are the reliability issues. And then in terms of in terms of architectural concerns, we're going to talk about post-training, systematic redundancy elimination in DNNs, and then synergistic co-design of sparse DNNs. So these are some of the pieces. So let's get started with the first top left guy over here. And the basic idea in this particular work is external invariance. So you're adding a little bit modular hardware over there. And this particular hardware is going to be able to provide you the ability to detect errors and tell you about what is going on in that particular sense, if you need to be concerned or not. All right, so what is happening over here and what is the basic idea? Well, take a look at the fully connected layer, and then you've got the weights and you've got the dot products. And of course, the dot products are a linear operation. So the dot products have linearity. Now, when you look at the convolutional layers, they look a little bit different, but at the end of the day, the computations that are happening over there are also linear computations of taking the products in this sort of matrix-like multiplication or tensor multiplications that are going on. Now, why am I emphasizing the linearity? Well, linear systems preserve this weight and input relationships at the outputs. So consequently, preserving this means that if I added a little bit extra spatial or temporal stuff, I should be able to have information over that that can protect me against defects escaping. And let me show you at the spatial level, what I can do is I can put an extra weight in this pink weight over here that you see. And if this sum of weights gives me 0, then the channel-wise accumulation will also produce 0. So consequently, by preparing and adding a little bit extra weights, I can get the outputs to have an invariant, a very convenient invariant of 0, and then check against this particular invariant and see if there has been any defects happening over here. Now, temporally, instead of adding an extra weight, what you can do is you can add an extra input, and you can do this again both for the fully connected and for the convolutional layers. And in this particular case, you don't quite have a 0 sum if there is a constant value because of bias effects and stuff like that. But nonetheless, in terms of invariance, the important thing is the constancy of the value that you expect, and then you can check against this particular constant value and find out. Now, these particular ideas are not tremendously new. I mean, these kinds of algorithm-based fault tolerance for matrix multiplication is something that has been going on for a while, and some of my good colleagues have been talking about this considerable amounts of time before. But trying to put this in there is a couple of contributions over here, and our contributions were more in showing that this worked in a neural network environment, particularly in terms of the convolutional stuff, which has its own complexity, and also you needed certain proofs as to how many errors you can accommodate and what combinations of errors can escape. So this is some of the work that we did. And in terms of hardware implementation, you have an adder tree and the processing elements, so you add a little bit extra that I'm showing in orange in order to accommodate this. All right, so this gives you a taste of this particular work. But this is external invariance, so you need to put a little bit extra to the hardware in order to do this. So once we did this work, then we realized, wait a minute, I mean, it's nice that you can put very small amount of hardware, and I'm going to show you the numbers in a few moments. But the next thing is, remember when I talked to you and I said, neural networks have a lot of redundancy. Now, what do we do with this redundancy in the neural networks? Okay, you need the redundancy in order to find your solution, but then you're stuck with it. Now, people have been dealing with this issue, and as I told you over there is all this quantization, there is the sparsity, pruning, all this work that has been going on in the literature. Now, this is very useful, but very quickly you realize that this particular work can help you to a certain extent, but you cannot get rid of all the redundancy over there. It's simply hardware-wise very inconvenient, because getting rid of random things throughout your neural network requires all kinds of hardware complexity of its own. So the bottom line is, the redundancy, we can get rid of some of it once we've trained the system, but we can't get rid. There is still appreciable redundancy left in your system at the end of the demo. We're going to get into this in more detail when we talk about the sparsity, hopefully. But considering that there is redundancy, and considering that you cannot throw away the redundancy, what is the next best thing we can do? But maybe use the plasticity of the system in order to guide it to take advantage of the redundancy to do something else that's useful. And the something else useful is the reliability. Maybe we can embed reliability through that redundancy that is always going to be with us. So this is where we change perspectives and we said, well, instead of adding extra hardware and taking advantage of matrix multiplications and linearity, can we guide the system to embed certain properties in itself so that it can detect errors, and maybe not only detect errors, but maybe even correct errors, maybe rectify the impact of the errors. So that was the perspective when we changed from the left to the right. All right, so our first steps over here were a little bit timid. And the timid step said, okay, let's put an internal invariant, a coarse invariant that maybe broke down this system. So we've talked about this, that broke down the system into two. And this breaking down this is sort of the computation, and the resulting activations are broken down into two groups. And we did arbitrarily somehow, let's say the first half and the second half. But somehow when we were training, we guided the system to minimize the differences between these two groups. So in other words, the difference of these two group activations were being driven down through a regularization term by using this extra part to the normally utilized cross-entropy loss minimization during training. And there is a little bit of a tuning coefficient to make sure the two constraints don't get into each other's faces over here. So this was the perspective, and training was utilized for embedding these invariants into the system. Now there is a little bit extra complexity because all this stuff is happening while you're training. The group differences will not be exactly zero. Number one, because during training you can drive it very low. Number two, there is numerical effects. So you need really to work in a threshold environment rather than an exact zero environment. So there is also questions raised in terms of false alarms and stuff like that. And I'm going to show you that this worked quite well. But for right now, to appreciate the challenges, you wanted to do profile thresholds and make sure that anything that exceeded that was seen as a faulty behavior. All right, let's compare the external guy with this other guy over here that is the internal invariant, a rather primitive internal invariant. And the first line is the critical error coverage. The external invariants did better than the internal invariants, but on many of these other things where you want to minimize, hardware cost, performance overhead, power and area overhead, you can see that the internal invariants, these are the blue guys, they're much better than the other ones. Okay, this is nice trade-offs and stuff like that, but the most important thing, guys, is not really the numbers that you see over here. The most important thing is that the left-hand side, all it can do is it can deal with the linear part of the system. The linear part of the system is all this dot producting that's going on. But the neural network is not only dot producting, there is nonlinear effects with all these values and between the layers and what's happening. And this is only possible to do with the internal invariance that you embed in the system. So there is a big difference in terms of the quality of what you are covering in terms of errors on the right-hand side. Plus you get a lot of area benefits and stuff like that. All right, so this is to give you a taste of the basic new idea that we were working with. Now, the second part over here, once this seemed to be successful, then the next question became in our minds, okay, this tells us that there is something wrong, right? Because all we could get from what I told you up until now is that if it exceeds the threshold, something is not computing right. But can we do better? Can we localize the error? Question number one. And question number two, if we can localize the error, maybe we can do something about that error. Of course, doing something is even harder than localizing, but one step at a time. All right, so can we employ internal invariants for error localization? So now the idea became, instead of doing this very primitive, this very coarse perspective, which said, break down things into two, and then make sure you train it so that the two guys become more or less similar in terms of their sums. Why don't we do much more fine-grained invariance embedded into the system? So can we put more fine-grained invariance into the system? And the basic idea over here is, well, let's put an anomaly limit in a local neighborhood sense. So you can have an anomaly detector where in a certain neighborhood you can examine 3 or 4 or 5 of those nodes and see if they fit a pre-described invariant that you embedded through training into the system. Okay, so if it exceeds, let's say, a normality constraint, then you say this guy has exceeded the normality constraint, and then there is the question of how do we rectify this particular guy. All right, so a number of different intellectual challenges come. One is expressiveness resilience trade-offs. So how do you set the maximum limit? So if the maximum limit is put in very loosely, then you can express more things in your neural networks, but at the same time more errors can escape because it's a looser constraint over there. So this is one thing to think about. Then the other thing is, what is the neighborhood? Is the neighborhood a neighborhood of 5, 7, 3? How narrow versus wide is this neighborhood? And this has an impact on some of those results. Okay, so those kinds of things just give you a taste of some of the stuff you need to ponder. But let me move on to the next question. And the next question is, okay, let's say we found that there was this node's result that was bad. What do we do about it? How do we rectify this particular problematic behavior? Now, normally in the world of semiconductors, all our strategies have been, we find an error, we correct it to what it was before. Completely. This is the whole theory of error correcting codes and replication and all these kinds of things. In neural networks, you cannot do this, you don't want to do this. I mean, it's really too expensive. And neural networks being approximate systems, you can be creative and do different approaches to this. If perfect restoration is not feasible, how do you do approximate error rectification? And this is the next topic over here. And to do cost-effective rectification of hardware errors, let's notice that the NM variables are clustered and centered around 0. So even stupid ideas like dropping work beautifully. You can, the minute you find an error, you can drop it, and as I'm going to show you the results are quite good in terms of accuracy. You can do other things. You can do clipping, medium filtering. So remember, there was this anomaly constraint that the system built in there automatically. So you can sort of, when you see something exceeding like this, you can clip it to the maximum level, and that works very nicely. So these are different approaches. So, and here is some high-level games that you can see how it works. So this is with a neighborhood size of 3 and medium filtering. So you can see this 129 over here has become through medium filtering 2.5. And so the error has been smoothed. And then, you know, similar things over here. So there is a number of issues to consider, which in a convolutional system, where do you apply? You want to apply it on the channel dimension, and that's because of the error density and neighborhood and various considerations. You want to do small neighborhood sizes, both to maintain content and efficiency, and small stride size. Perhaps an important thing is during training what happens. And during training, your problem is that these medium filtering are step functions. Step functions are bad functions because they have this discontinuity in the gradient derivative sense. So what you want to do over here is you want to maybe use something like a sigmoid in order to do gradient propagation and stuff like that. 5 minutes? Are you sure? I mean, 15 minutes? In 5 minutes, I should.
Maybe a little bit more, yeah.
Oh, okay. Well, guys, I mean, I was going to show you the results, but
Please.
the results will take 5 minutes. So, believe me, the results are great. Let's move on from the results so that I can show you at least something that has a little bit more intellectual part over here. This is also the hardware implementation. Maybe we skip that as well, and let me show you at least some ideas by talking a little bit about proactive vulnerability reduction of the systems. All right, so this is now what you have seen is, you know, these neighborhoods building in invariants so that you can prepare systems for catching errors when they happen. And different perspective is, instead of catching errors as they happen, why don't we make the systems not be vulnerable to errors? What does this mean? Well, let's take a look at this particular part and think a little bit about signal-to-noise ratios. So if the signal-to-noise ratio in a noisy environment is large, then information recovery is easy. But if the signal-to-noise ratio is small, then information recovery is difficult. So this is very basic ideas over here. So how does this impact our neural networks? Well, the important thing to figure out is the relative error magnitude is proportional to the impact on the DNN functional outputs over here. So why is this perspective important? Well, take a look into DNN and quantization. So normally what we do is we use quantization in order to reduce the hardware precision requirements. So these are the quantization points and boundaries that we cut the system and reduce the numbers over here. But the quantization impact on reliability issues has not been well explored. So what is the impact that one should think about? Well, take a look at this. So you have a hardware range, and the hardware range may be a certain number of bits and the same number of bits and for each of those particular layers. Now, in some layers, you may end up using the whole hardware range, but depending on the layer, you may end up using much less. Now, as a matter of fact, not only you may use much less, in some cases, if you took out the outliers, then the range may become even smaller. So one can see what you can represent and how much you're using may be very different things over there. Now, why is this important? Well, the reason why this observation is important is because this empty space that you see over here on the left and the right of the blue line, those are bits over there, and those bits are prone to errors, and those errors, normally those bits will be 0 because you don't represent anything. Well, if it's a negative number, it will be 1. But if they flip, they will make a huge difference into what you're representing. So they're sitting over there making the whole system very vulnerable to errors. All right, so what do we do about it? Well, so what we want to do is, we want to resize this by changing the representational scheme by having certain scaling factors over here to match the layer range, number one. And number two, we want to get rid of the outliers during training and sort of push the system to having less outlier representation so that you don't have to stretch the particular representation range and make things vulnerable to errors. So these are the basic ideas over here where you play with this. And let me show you here very quickly the behavior of the systems. So this is 10 times the global range that you need. This is the behavior that you are seeing in terms of degradation when errors happen. I mean, the horizontal part over here is the amount of errors that ranges from 10 to the minus 5 to 10 to the minus 1. And you can see as the number of errors go higher and higher, you get the whole accuracy curve, you know, shrinking down to pretty much very low levels. So this is with 10 times global. Now, this is what you see with global. So if you cut the 10 times effect, so then if you do it layer-wise, this is how the curve becomes able to tolerate more and more errors. Now, if you use standard regularizers like L2, L1, and others that have been in the literature, you get a little bit better, but not much better. So you really need to come up with outlier regularizers like max squared or max magnitude regularizers, and those give you much better results. And this is sort of how to make systems less vulnerable to errors. Now, there is one more piece over here about the yield improvement, and then there is all the architectural stuff. But you said 5 minutes, and that's the end of 5 minutes. And I think there is another 45 minutes over here. So maybe we stop and talk about it some other time in this universe.
Because yeah, there's our department head is waiting.
Oh, all right, we better stop.
Yeah.
Department heads are important.
Yes. So, yes. Okay. I thank everybody for being here. Actually, you know, it's unfortunate that we didn't hear the full presentation, but I got a lot of inspiration for new topic. I mean, I've been working on improving accuracy, and this gave me some inspiration about fault tolerance and security. So maybe that could be a sort of added characteristic that we can all work on doing our research. Okay, so it's not you know, accuracy or precision or efficiency, but I think fault tolerance, reliability is very, very important. And maybe those characteristics needs to be studied and observed, and maybe we should focus a lot on this topic, okay? And I appreciate Professor Aurelio Gou for giving this wonderful talk. And we will have this video available, and I think if he's kind enough, he may share his slides with all of us.
Yeah, I can send you some PDFs.
Okay. Let's give
thank you for coming to my door.
Yes.